Gravity is not a force. Hello, what? This might be the expression of many who are watching this video. But don't worry, you will surely happen to know the reasons behind that line. Just make sure that you watch the entire video. Gravity is one of the most popular concepts of the world. It is the reason for our weight, attracts objects towards the ground, and many more. But how long do we know about it? It all started under a tree with a man holding an apple and thinking why. If it was not for that apple, most of the pages in our science books would have been empty. But we knew what happened. The falling of that apple raised a question in Isaac Newton's mind, which led to our topic gravity. According to Newton, gravity is an attraction force that every mass possesses with respect to the other mass, and he stated an equation calling it the equation of universal gravitation. In this, G is called universal gravitation constant. It works fine in cosmic scale, but when we apply it in real life situation, we can't find the gravity between people or other masses on Earth because the Earth dominates the others with its massive weight. So we use acceleration due to gravity to perform calculations of gravitation on Earth. But there are some gaps that needed to be filled. At that time, Einstein came up with his general theory of relativity that just opened the human eyes to see the magical cloak of cosmos. The fabric of that cloak is made up of space-time together, forming space-time curvature. This concept is explained by Hermann Minkowski, about which we will discuss on later videos. According to the general theory of relativity, gravity is not a force but a natural phenomenon that forms when mass or energy disturbs the space-time curvature. Einstein first explained it with a freely falling person. When a human is falling freely, he never experiences the impact, but he accelerates. He feels the impact only after reaching the ground. This observation gave a conclusion that gravity and acceleration are two sides of a single coin. But when a rocket is about to fly, the astronaut in that rocket feels the impact. That impact is equal to the Newtonian gravitational force. This raised a question: is this a coincidence? Yes, it is. When a rocket is about to fly, the body of the astronaut starts from the rest and gets to motion, but the body of the astronaut tends to be at rest due to inertia. So what the astronaut felt was the inertial force that is equal to the Newtonian gravitational force. This conclusion acted as a base to the general theory of relativity. Einstein believed that nature's laws are one and the same for all types of objects. According to the first law of motion, there is no force acting on an object if it is moving in a straight line with constant speed. But in the world, there are all sorts of non-uniform motions. The simple motion of a globe to massive movements of stars and planets is non-uniform. There is only one thing that moves with constant speed in straight line, that is light. So he stated his first prediction on light. According to his prediction, the light bends near a star or planet due to gravity, as the space-time is wrapped around it massively, and he proved it. Hence, gravity is not a force as it is acting on light which is moving in a straight line with constant speed. So what is meant by the gravity actually? Here is how it works. The space-time is a flat plane that is made up of a stiff cloth tied between the ends that we can't see. So when mass or energy is placed on that cloth, it bends. This bend brings the objects above it towards the center. But the individual objects that are being attracted have their own bends that attracts nearby objects. This forms a network of systems like solar system and galaxy. This phenomenon of formation of bends in the space-time due to mass or energy is called the gravity. After his prediction is proved, he tried to calculate the extent of gravity. So he formulated an equation using tensors. He called it Einstein's field equation. He applied it in many situations and compared with Newton's. His equation worked even where the Newton's formula failed. But when he applied his equation to the whole universe, he found that universe is unstable. It might be contracting or expanding. So he added a cosmological constant using lambda, which later renounced after modern cosmologists found evidence on expanding universe. Even after these many years of general theory of relativity, we study Newtonian gravitational theory in our books. Because most of the calculations that we do is for approximations that Newton's theory can handle. And when we need perfection, we prefer Einstein's theory of relativity. Einstein also stated about the existence of black holes, gravitational time dilation, and many more fascinating concepts. So what are you waiting for? Hit the subscribe button for more fascinating and magical concepts of the universe. Give a thumbs up if you like the video and state your opinions in the comments. This is Mani Prakash signing off.